Okay, greetings to all of you. In the last video, we have solved the first two problems on the textbook. In this video, we will be solving a few more problems. So let's start with the third question. They say that an n-type piece of silicon with a length of 0.1 micrometer and a cross-section area of 0.05 micrometer whole square, and it sustains a voltage difference of 1 volt. So they say that they have applied an external voltage of 1 volt. That means, and this is an n-type, so the current will be drift current. Majority of the charge carriers will be uh, acceptor atoms, that means electrons. Sorry, donor atoms, that means electrons. So they gave the doping level concentration, that means number of electrons Nd equals to 10 power 17 centimeter cube. We need to calculate the total current flowing through the device at t equals to 300. So drift current is due to only electrons and the whole current is negligible. It can be written as VANQ. V is mu E. As the current is reverse from the electric field, we can write it as negative. And area NQ. Okay, plugging these values in these formulas, we get 1350. I'll write units in the end, and its electric field will be voltage by length. It is 1 volt by 0.1 micro, and area is 0.05 micro whole square. N is 10 power 17. Q is 1.6 into 10 power minus 19. And the units are 1. This is 1 centimeter per volt second, and this is 1 by 1 volt per 1 meter. This is meter square area, and this is 1 by centimeter cube, and this is coulomb. Coulomb by second is ampere, and meter and 1 meter can be cancelled. Voltage can be cancelled. Centimeter can be cancelled. So this is 100. We have a 100 factor here. So yeah, plugging these values in our equation, we get 1350 into 0.05 whole square. This 1 micro can be cancelled into 10 power minus 12 into 10 power 17 into 1.6 into 10 power minus 19 divided by 0.1. We did a mistake somewhere. Into 100. Okay. 1350 into 0.05 whole square. Okay, this is not 10 power minus 12. This is 10 power minus 6. So it's a 54 microampere. Okay. Now let's go with the second part of this question. They told repeat A for T is equals to 400 Kelvin. Assume for simplicity that mobility does not change with the temperature. They told to repeat this calculation when the temperature increased. Basically, whenever the temperature is increased, the total number of charge carriers in the intrinsic semiconductor will increase, but the doping concentration remains the same. Okay. So if Ne remains the same, Ni square will change and Np will change, but Nd will remain the same. So that means the current also remains the same. Okay. Yeah. Now let's go to the fourth question. The fourth question says, from the data in problem 1, repeat the problem 3 for germanium. Assume mu n is 3900 centimeter per volt second and mu p as 1900 centimeter per volt second. nu E is equals to 3900 centimeter square per volt second. We need to repeat the problem 3. That means this. Okay. Okay. So the I drift will be negative 3900, same 0.1 micro and 0.05 whole square micro square 10 power 17 into 1.6 into 10 power minus 19 into 100 ampere. That will be it will be 156 micro ampere. This is part A. Similarly for part B, uh, they increase temperature to 400. See, that means the number of electrons remains the same because that has been doped, but number of hole concentration will increase, but that will be negligible as the product NP into Ne is equals to Ni square. As long as this equation holds true, if this is constant, these both will change, keeping the multiplication constant. So the current will remain the same. Okay, because majority of the charge carriers are electrons. A small increase in hole concentration won't change the current. Okay, now let's move on to the next question. They say in the figure 2.37, it shows a p-type bar of silicon that is subjected to electron injection from the left and right. Okay, and okay, electron from left and hole injection from right. Determine the total current flowing through the device if the cross section of area is 1 micrometer. Okay, they told area as 1 micrometer whole square. So we need to calculate. Okay, there is no external voltage, so the current will be due to diffusion. So current due to diffusion will be dn by dx minus dp by dx into A into Q. Okay. Okay, for the first concentration profile, concentration gradient profile, the slope will be, as the profile follows this line equation y equals to mx plus c, their slope will be just m. Okay, so diffusion constant for electrons will be 34. I'll write equations in the end, and slope will be y2 minus y1. Let's say 2 micrometer will be x1 y1, so y1 will be 0. 5 into 10 power 16 will be x2 y2, so y2 is 5 into 10 power minus 10, 5 into 10 power 16 minus 0 by 0 minus 2 micro minus dp is 14, dp by dx is 2 into 10 power 16 by 2 micro minus 0 into area. It's 1 micro whole square into 1.6 into 10 power minus 19. Now writing units in the end, we get 34, it's 1 centimeter square per second. This is centimeter power minus 3 by this is 1 meter. This is meter square and this is coulomb. So coulomb per second is ampere. 1 meter will be cancelled. This will be 100 centimeter. Centimeter cube can be cancelled. So we have 100 ampere. Now let's plug these values in calculator. Okay, so the mistake is here. The mobility of the holes will be 12 centimeter per second. It's not 14. So plugging these values in our calculator, we get 34 into 5 into 10 power 16 by 2 into 10 power minus 6 plus 12 into 2 into 10 power 16 by 2 into 10 power minus 6. Okay, we get 9.7 into 10 power 23 into area 10 power minus 12 into 1.6 into 10 power minus 19 into 100. Yeah, so it's 15.52 microampere. Okay. Okay, when this will be negative. Okay, yeah, we have solved 3 problems now. Let's solve more problems in the upcoming video. So make sure you stay tuned and follow along with the series. Thank you. Bye. We'll see you in the next video. Bye.